All right, so now that the diagnostics are on, we can see that we get an R value of 0.95. Okay. And that's a strong correlation, isn't it? I mean, if we take a look back at these examples here, 0.95 is quite close to 1. It was positive like we expected because it's moving upwards. Definitely stronger than this. We get a correlation coefficient of 0.95. But then we ask the question, well, really, we aren't able to record the number of chirps at every possible temperature, at every possible time. We're really just dealing with a sample here. So can we apply some inferences into the actual population and how strong that correlation really is? Is this 0.95 just by chance because of, where did it go? There it is. Did we just happen to get a few of these points a little bit closer together than they would have normally been? You know, what's really going on here? Can we use the sample to make an inference about the population? And here's how we're going to do that. Okay, we're going to use the correlation coefficient R, okay, from our sample to determine if P, which is the population correlation coefficient, also called Pearson's population correlation coefficient, is it significant enough? And what does that have to deal with? Well, we're going to have to consider what the sample size is. That's going to be part of it. We know that the greater the sample size is, the more confident we are in the result that we got from our sample. The smaller the sample size, the less confident we are. So what we'll do is we'll set our level of significance at either 0.01 or 0.05. We're going to be using a table from the back of the book. Those are the two values. N is the number of pairs of data in the sample. So how many pairs of data do we have? That's our N. Okay. We'll use table 11 in Appendix B to set our critical value. So in the back of the book, I see that on page A26. Okay. So right here, table 11, you'll notice that the headings are N, alpha equal to 0.05, alpha equal to 0.01. So again, you'll just set your level of significance, you'll find your number of data pairs, and then you'll find what our critical value is. Now, all the critical values in the table are positive, okay? It doesn't consider negative. So what we have to do is we have to look at the absolute value of R, and if absolute value of R is greater than the critical value, then the population coefficient P is significant. There is significance to that. One thing here, and I hope you're open to your book by this time, you will notice, okay, that the critical values for a small number of data pairs are really high. We have to beat, like when I look at N equals 4 with a level of significance of 0.01, okay, we have to beat 0.99. So like if I went where it is, so if we set our alpha, our level of significance to be 0.01, then the critical value is equal to, well, let's see here, I shouldn't be on this page. Let me just go to another page here. If N equals 4 and our level of significance is 0.01, then our critical value, okay, is 0.99, which means our absolute value of R, our correlation coefficient from our sample, has to be greater than 0.99 to really say that there is a significant correlation in the population. Drop my pen. Variables. Okay. Why is that? Well, if we only have 4 points, right, could we randomly fall pretty close to the line? Well, what happens if this 1 point here was there? Does that totally change what looks like the trend of what was upward to downward? Right? So what you're basically saying is with 4 data points, you have to have a perfect line to say that there's significant correlation in the population. The sample size is just so small. So let's go back to this one. What is our N? How many data pairs did we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So n is 9. Let's set our correlation, our level of significance to be 0.05. So then when we look at our table and we find 9 and we go to 0.05, our critical value is equal to 0.666. Now our correlation coefficient was already positive, and if we take a look at that, the absolute value of our correlation coefficient, I'm just putting the absolute value in there just in case it's negative, is greater than 0.666. So what does this show us? What is our conclusion? Our conclusion is that there is a significant correlation between temperature and chirps in the population. Now, what's the likelihood that we're wrong? Remember that the level of significance is the likelihood that we are making a mistake when we state that conclusion. All right. So, let's look at one more example. An economist wants to determine whether there's a linear relationship between a country's gross domestic product, okay, gross domestic product, GDP, and this should say carbon dioxide emissions, which would be CO2. So basically, this is the gross domestic product, the amount of money that's generated within that country. Okay. Is there a relationship between that and the CO2 emissions, like how much CO2 gases we're sending into the atmosphere? So determine if the correlation coefficient is significant at 5% level of significance. So we have some countries here. We do not have every country. This is a sample. We have their GDP, and then we have their CO2 emissions. What we'll do is we'll put those into the calculator. We'll calculate our correlation coefficient. Then we'll find our critical value from the table in the book, and we'll make our conclusion. So I'm going to pause the video. I'm going to put this into list 1. I think this would be our explanatory variable here, that the more that we're generating in our country from a GDP standpoint might explain why our CO2 emissions are greater. So I'm going to choose that to be my response variable Y. So I'll pause the video. If you want to do the same and put them in, you're welcome to do that. All right, so I have them in. Let me just make this a bit bigger for you guys. Now, our plot 1 should still be on, right? If I go into y equals, our plot 1 is still on, which still had a list 1 and list 2 set up, so that's good. What I'm interested in here is changing the window, and our GDPs are small numbers. Now, they're not really small numbers because this is in trillions of dollars, but in trillions of dollars, they're small numbers. Let's go 0 up to, let's go 7. Let's go by ones. Our CO2 emissions in millions of metric tons are ranging from 253 up to almost 1,200. Let's go 0 to 1,500. There we go. And let's send that one by 100s. And let's hit graph. Okay, so it looks to me like there is a relationship. Let's see how strong that correlation is. So we are going to quit out of this. We are going to choose stat, calculate. We're going to choose linear regression. All that looks good. Let's calculate, and we get an R value of 0.912. Okay, let's see here. How many data pairs do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Our level of significance is set at 5%. So we're going to go to the table here. I'm going to go down to n equals 10. And we get a critical value equal to 0.631. 2. And it makes sense that it's slightly smaller than the last one because we've increased our sample size a little bit. So we can be a little bit more confident. We still have the same level of significance from the last one. Now again, our absolute value of R is greater than the critical value. So the relationship between GDP and CO2 emissions shows a significant correlation. And there we go. All right, thanks for watching. We'll see you. Oh, do I have one more? Oh, I have more stuff to talk about. We got to be really careful about something. Read this headline. Correlation does not mean causation. We are measuring the relationship between the two. It does not mean that one causes the other. So when we go back to this last example, we found that increasing the GDP is increasing the CO2, but is it causing it? Okay, there's that relationship, there's a correlation there, but is it causing it? That we don't know. That takes further exploring and investigating. So here are some questions that we should be asking ourselves. Is there a direct cause and effect relationship? It's very possible that there is that direct relationship where this one is causing, this one increasing causes that one to increase, or this one increasing causes that one to decrease. That's possible. However, it's also possible that it could be a reverse cause and effect, that we thought this was the explanatory and this was the response, but it could be the other way around for a cause and effect. It is possible that the relationship can be caused by a third, this should say or, not row, a third or a combination, well, it's really struggling to spell, a combination of several other variables. I don't think in this last one that GDP causes CO2 emissions, right? But could there be a lurking variable in there that is causing the CO2 to go up and is related to the GDP? So there could be other things that confound the situation, or it could just be coincidence. So do not make that mistake of saying, yes, there's a correlation, so this causes that. Right? I could probably find data where, let's say, as ice cream sales increase, the murders in the city increase. Okay, there could be a correlation between those two. It could be totally coincidental. Okay, but we'd be certainly careful not to say that increasing ice cream sales increases murders, right? That doesn't seem like that would make much sense. So we have to be really careful about the things that we're using correlation for. So just be aware of that. We'll have more conversations about that as we go on. See you later.